the efficiency of a transformer. The efficiency of a transformer is always less than 100% because of the losses in the transformer. The efficiency of a transformer is defined as efficiency is equal to output power over input power times 100%. It can also be defined as efficiency is equal to power in the secondary coils over power in the primary coils times 100%. That is, the output power is the power dissipated in the secondary coils, while the input power is the power dissipated in the input coil. So these are the formulas that we can use to calculate the efficiency of the transformer. Now let's take some calculations on the efficiencies of a transformer. Example 1. Find the turns ratio in the transformer which delivers a voltage of 120 volts in the secondary coil from a primary voltage of 60 volts. So what we're going to do, we're going to use the turns ratio is equal to NS divided by NP, which is also equal to ES all over EP. So the turns ratio can be calculated using this formula. Since we are given voltages only, the primary voltage is 60 volts and 120 volts represent the secondary voltage. So therefore this is going to be equal to 120 divided by 60. So this is going to give us 2. So the turns ratio is 2. Example 2. A transformer with 50 and 300 turns is used to step down 300 volt AC. 1. Calculate the output voltage. 2. Explain why the measured value of the output voltage would be less than the calculated value. 3. How could the difference be reduced in practice? Okay, here we are told that a transformer with 50 and 300 turns is used to step down a 300 volt AC. So since it is a step down transformer, then the number of turns in the primary circuit should be greater than the number of turns in the secondary circuit. So it therefore means that the number of turns in the primary coil should be equal to 3000. So you should take note of this, and the number of turns in the secondary coil should be 50. Then we use it to step down a 300 volt AC. So this one is the 300 volt is being stepped down. So the primary EMF will be 300 volts. So we have to calculate the secondary EMF, which is stepped down. So we're going to use the formula ES all over EP is equal to NS all over NP. So from here we have to look for ES. So we are going to make ES the subject of the formula. So ES would be equal to NS times EP divided by NP. So that will be equal to NS is 50. So we're going to have 50 times EP, the primary voltage, which is 300, divided by NP, number of turns, which is 300. So by working this out, we're going to have 50 times 300 divided by 3000, and that is equal to 5 volts. So the output voltage, that is the voltage in the secondary circuit or coil, is 5 volts. Now to answer the second part, explain why the measured value of the output voltage would be less than the calculated value. So there is energy losses in the transformer core and windings. So that is the reason. So we know the different types of energy losses in the transformer. So for the 3, how could the difference be reduced in practice? So the difference can be reduced in practice by 1. A, by laminating the soft iron core to reduce eddy current losses. B, by the use of special alloys or soft iron cores to reduce hysteresis losses. 3, by the use of thick wires or low resistance coil to reduce heating in the coil or to reduce I-squared arrow losses in the form of heat. And finally, by the use of special coil windings or efficient coil designs to reduce the energy loss by flux leakage in the primary circuit. So basically, these are the 4 types of energy losses that will tend to reduce the efficiency of the transformer, or that will reduce the calculated value of the voltage because of all of these losses in the transformer. So by correcting each of the losses, we'll be able to reduce the difference in the value. Next, 3. Draw a simple labeled diagram illustrating the principle of a step-down transformer and explain how it works. So I'm going to draw a step-down transformer. Basically, I'm going to draw an iron core, a soft iron core. Okay, this will represent my soft iron core. Then we are to use it to make a step-down transformer, meaning that we are going to have a higher number of turns in the primary coil, and we are going to have a lesser number of turns in the secondary coil. So basically, this is a transformer, so we can label this as ES, EP. So this is the soft iron core. So basically, this is a step-down transformer because we have a higher number of turns in the primary than that of the secondary. So how do we now use it? So state 3 ways, okay, to illustrate and explain how it works. Basically, how it works is that we have a higher number of turns in the primary circuit than the secondary circuit. When an alternating current is applied at the primary coil or circuit, an alternating or changing EMF is produced in the soft iron core of the transformer. This changing magnetic flux then links the voltage to the voltage in the secondary coil, or induced an EMF of the same frequency as the one in the primary coil. So the induced EMF will be smaller than that of the input EMF because it's basically a step-down transformer. Okay, B, state 3 ways by which energy is lost in a transformer and how they can be minimized. I think that was explained in the previous example. So you go to that place and look at the ways in which the transformer losses, energy can be lost in transformer and how they can be minimized. The 4 ways we have duly explained in that question. So C, if a transformer is used to light a lamp rated 60 watts, 320 volts from a 240 volt AC supply, calculate 1, the ratio of the number of turns of the primary coil to the secondary coil in the transformer. Now, take a look at the question. You have to calculate the ratio of number of turns in the primary coil to the secondary coil. It's not the turns ratio, but you have to calculate the primary coil ratio, turns in the primary coil to that of the secondary coil. So the ratio CI, so the ratio would be NP all over NS, and that would be same as EP all over ES. So depending on what you are given, you can actually calculate this using that. So the question is, a transformer is used to light a lamp rated 60 watt. So the lamp will be connected to the secondary coil, and the transformer receive 440 volts AC from the mains supply. So the primary circuit receive 40 volts. So that will be 440 volts rather. So that will be 440 divided by 220. So that ratio, the primary ratio to secondary ratio, would be equal to 2. So that's 2. Now remember, the ratio you are asked to calculate was the primary coil to secondary coil ratio in the transformer, not the turns ratio. If you had to be turns ratio, that ratio will be 1/2, because the turns ratio would be NS all over NP, which is the same as ES all over EP. So you're not asked to calculate the turns ratio. So 2. Current taken from the mains circuit if the efficiency of the transformer is 95%. So here we're going to use the efficiency formula, either this power output over power input times 100%, or efficiency equal to power input in the secondary coil all over power in the primary coil times 100%. So we'll just use any one of that. So in this case, the efficiency would be the power in the secondary coil will be, okay, we're giving the power output in the secondary coil as 61, will be 60 watts all over the power in the primary coil would be the voltage E primary times I primary times 100%. So 95% is simply 0.95. I will just omit the 100 from it, so I get 0.95 is equal to 60 all over the primary voltage is 440 times the primary current IP. That's what they asked us to calculate the current taken from the mains. The current taken from the mains means that the current that the primary circuit or the primary turns of the transformer takes from the main circuit. Okay, so when we work this out, this is going to be equal to, so I'm going to have 0.95 times 440 times IP will be equal to 60. I'll just multiply this out. 0.95 times 440, that's equal to 418 IP, is equal to 60. So from here, IP would be equal to 60 divided by 418, and that will be equal to 60 divided by 418, 0.144 amp. I'm giving this to 3 significant figures. Okay, for question 4, a transformer supplies 15 volts from a 220 volt mains. So the transformer supplies 15 volts. It gives out 15 volts. So the secondary voltage is 15 volts from a 220 volt mains. So the primary voltage is 220 volts. So EX is equal to 15 volts and AP is equal to 220 volts. If the transformer takes 0.7 ampere from the mains, so the input current, that's the secondary current, the primary current rather, would be 0.7 volts. So I primary is equal to 0.7 ampere rather. Okay, from the mains when used to light 3 lamps connected in parallel and each rated 15 volts, 440 watts. Okay, so I'm going to draw a circuit for this. The circuit has we have 3 lamps connected in parallel. So my lamp is going to be like this. This is the first lamp. Okay, the second lamp. Mind my diagrams. uh, the third lamp, okay, all connected in parallel. So I'll just draw a simple circuit to represent this. So for the circuit, they are all rated, okay, each rated 15 volts. So the voltage across each of the lamp, since the parallel circuit, the combined voltage, the output voltage, ES is 15 volts as stated, and we have 40 watts of energy on this, 40 watts on this, we have 40 watts on this, we have 40 watts. So the energy of each of the lamp is 40 watt. So the current flowing through each of the lamp, we're going to use from power formula, P is equals to IV. So from here you can see that I will be equal to power divided by voltage. So each of the power in the circuit, or each of the current in the circuit, will be equal to, since they are all the same, they have the same power and the same voltage across them is 15 volt. So since they have the same power, we're going to have 40 divided by 15. So I would be equal to 40 divided by 15. That's 2.67 ampere. So I'll take this to three significant figures again. So I'm taking this to three significant figures. So since there are three of them, the total current in the secondary, IS, will be 3 times 2.67. 3 times 2.67. So that's going to give me 8.01 seconds. So that's the secondary current. You can just add all the currents together, just to I1 plus I2 plus I3, because the current, total current I here is going to be I1 plus I2 plus I3. Since they are the same, just multiply the two together. That gives you the current in the secondary circuit. So let's calculate the efficiency of the transformer. So the efficiency of the transformer would be power in the secondary circuit, power in the secondary, or power output, and that would be the voltage in the secondary circuit. That's ES times IS all over EP times IP times 100%. So that's the EP and times IP is the primary power output. Okay, it's the primary power output. So this efficiency would give us ES is 15 times IS 8.01. Just work all my values to three significant figures, divided by EP, which is 220 volts from the question. So we have 220 times 0.7 times 100. Just multiply the denominator and the numerator, then also multiply the denominator. So that's going to give us 15 times 8.01 times 100. That's equal to 12015 divided by 220 times 0.07 times 0.7. 0.7. So that's going to give us 154. So I'm going to divide 12,015 by 154. 12,015 divided by answer. So that's going to give me 78%. So I'll leave this to the nearest whole number. So that's approximately 78%. So that gives the efficiency of the transformer. Now the next question is the cost of using it for 24 hours at 30k per kilowatt hour, 30 kobo per kilowatt hour. Now the question, you have to take note of the question again. The question is the cost of using it. What is the it? The cost of using the transformer. So the transformer will develop power in the primary circuit. It's not the cost of using the lamp. Okay, the cost of using the lamp will have to do with everything on the secondary circuit. So then we're going to calculate the power developed in the primary circuit in kilowatt. So power in primary circuit developed in primary circuit will be equal to ES times IS. So that will be 220 times 0.7, and from our previous calculation, that's going to give us 154 watts. Okay, so that's the power calculator, 154 watts. Then to convert this to kilowatt, we divide it by 1000. So I'm going to divide it by 1000, and that's going to give me 0.154 kilowatts. Okay, so we want to calculate the cost of using it for 24 hours at 30 kobo per kilowatt hour. So we got 0.15 kilowatt hours. So for 24 hours, kilowatts rather. So for 24 hours, it's going to be 24 times 0.154 times per 30 kobo times 30 kobo. So that would be the cost. So let me just write it there, the cost for 24 hours. So that's going to be 0.154 times 24 times 30. That's equal to 110.88 kobo. We can divide this by 100 just to convert it to naira. So that will be equal to 1.11 naira, approximately 1.11 naira. So that gives the answer to this. Okay, next question. Draw a label diagram to explain the working of a transformer which can produce 24 volts from a 240 volt supply. So this is a step-down transformer. The explanation is a bit different from the previous explanation because here you have been given the values for the voltages. Okay, so what we're going to do is this. We're going to draw a step-down transformer again. So the first thing you have to do in drawing a transformer is to always draw the iron core. So this is my iron core. Am I my drawing? So since it's a step-down transformer, I'm going to have more turns in the primary coil. Okay, then I'm going to have less turns in the secondary coil. If possible, you could calculate the turns ratio and just draw the number of turns based on the turns ratio. So I'm going to calculate the turns ratio. So the turns ratio would be equal to, so we are given the voltage, it's going to be ES all over EP, and that will be equal to, so we have to produce 24 volts, we have 24 all over 240. So that's going to be equal to 1 over 10. So what that means is that when this is going to be 10 tons, we're going to just have 1 ton here, or a multiple of 10 for this. Whatever this is going to be, the primary coil is going to be 10 times more than the secondary coil. So that gives us the turns ratio. So we've drawn so you can put the labeling. So we have EP, ES, the transformer core, soft iron core. Then okay, let's just explain how we can convert that. So what we do is that the explanation simply means that we're going to have a transformer having 10 times the turns in the primary circuit compared to the secondary circuit. So that's basically what you should do. So there's going to be 10 times the turns in the primary circuit coil than the secondary coil. Okay. B, if the efficiency of the transformer is 80% and the current in the secondary is 10 ampere, calculate the current in the 240 volt supply. So let's quickly work this out. B, if the efficiency of the transformer is 80%, so we have 80 is equal to, and the current in the secondary is 10 ampere. So we know that the power output will be the secondary voltage 24 times the current in the secondary coil 10 all over the primary voltage 240 volts times the primary current divided times 100%. So we can just work this out from here. So this is going to give us 80 is equal to 240000. Okay, when you multiply this at 240, that's 24 times 10 is 240 times 100, that's 24,000. Okay, so we're good with that. So divided by 240 IP. So just take IP up. So IP would be equal to 24000 divided by 240 times 80. So that would be 24000 divided by 24 times 2000, 240 times 80. So that's 19,200. So I'm going to do 24,000 divided by 19,200. So that's equal to 1.25 ampere. So that's 1.25 ampere. So the current in the primary circuit is 1.25 ampere. So we have to the last part of this question is that we have to give reason or give two reasons which explain why the efficiency of the transformer cannot be 100%. I think we have already explained this in our previous question, so one of the previous questions. This is simply because there are transformer losses, and you can go back to that question and look at the various transformer losses.